Welcome student. Use of acetylene is the next topic in our video lecture series for PCH 4802 Unit 3. I am Dr. Devang Pandya, Department of Chemistry, St. Xavier's College, Autonomous, Ahmedabad. Well, point to discuss in today's lecture. We'll start with the introduction of how to use the acetylene in organic synthesis, and we'll give certain example like use of acetylene in the synthesis of oblivion, reduction of alkynes to alkene, synthesis of dienes, ketones by hydration of acetylenes, and in the last point we're going to discuss an alkyne containing anti-AIDS drugs synthesis as well. Well, in this uh, use of acetylene in the organic synthesis, we shall look at one's class of starting material as alkyne or acetylenes and see what special job this alkyne and acetylene can do in the synthesis. In particular, we have to see how they can solve some problems and how they can cater that problem and solve the synthesis and make it a little bit easy. Acetylene, as you can see in the structure 3 itself, is readily available and commercially available, and that is why it is the first choice for the organic synthesis, and its important property it has that property is that it going to gives us a protons on a triply bonded carbon system, which are much more acidic compared to the most of the carbon hydrogen containing proton. Acetylene forms a genuine anions that you can see in the structure 4 with sodium in liquid ammonia, a lithium derivative that is in a structure 1, and butyl lithium, or we can say a Grignard reagent that you can see in a structure 2 by reaction with simple alkyl Grignard such as ETMGX, and that is how acetylene is going to be more important uh, starting material for different organic synthesis. You can see here these derivatives react with the type of carbon electrophiles we have already met, such as alkyl halides, aldehydes, and ketones and epoxide to give structure 5, 6, and 7 respectively. Here we will going to see the use of acetylene in the synthesis of oblivion. Oblivion is clearly an adduct of acetylene and ketone, that is structure 9. And the synthesis is trivial synthesis, that means it is done old trivial way. This example and the next are from the patent literature. You can obtain it from patent literature, and so we are amazing. We are assuming that at the details there is no yield is going to be obtained. These products still have an acidic hydrogen on the triple bond, so they can um, react with the base and electrophiles. We have another example of the use of acetylene in synthesis of surfenol. Surfenol is clearly an acetylene diadduct with the same ketone, that is structure 11, being used twice, and that way we can synthesize these two important molecule. This time a second treatment with base will be needed to make the second anion, uh, as hydroxyl proton in structure 12 is more acidic. We can say it's having a pK value near about 16 than the alkyne proton, which have pK value near about 25. So two molecules of base will be needed, and the most reactive anion, uh, that is alkyne, react first, and we're going to get the product. Next is the reduction of alkynes to alkene. Uh, in the reduction of alkynes to alkene, we can see the acetylene adducts are important in their own right, but they are valuable intermediates because distributed acetylene that you can see in structure 15 can be reduced at with to either E or Z isomer of alkenes by different reducing agents. Catalytic hydrogenation using the Lindlar catalyst to stop reduction to alkane adds a molecule of hydrogen to one side of the triply bonded acetylene to give Z isomer, that is structure 14. Addition of solvated electrons formed when sodium metal dissolve in liquid ammonia may give the dianion, that is structure 16, with the two negative charges in sp2 orbitals as far from each other as possible, and certainly it gives isomer E, that is structure 14, on protonation with a weak base such as tertiary butyl hydroxide. We can see here in this cis selective reduction, when we made compound structure 13, we're going to obtain earlier the starting material cis butanediol, that is 18, is readily available as it is made by the Reppe process. So the structure 18 can be obtained using the Reppe process. There is a there is a story of the reluctant Reppe not divulging the detail to the allies after the Second World War. An unsymmetrical example is the allylic halide, that is structure 19, needed for the synthesis of cis-jesmone. Uh, Obvious disconnection takes back to 21, that is structure 21, and a simple three-component synthesis is going to be obtained. As an alcohol, that is structure 22, was available, it was simply a case of putting in the ethyl group. Of course, the alternative order of event may be a better option, since the reduction to the cis alkene can be done either before or after incorporation into the cis gismone skeleton, that is structure 22, was also transformed into the propargylic bromide, that is structure 24. The trans acetate, here you can see structure 25, is the pheromone used to trap pea moths. Pheromones are the compound which is going to trap moths or insect attractor, they are known as. Changing the E isomer of alkene into the acetylene allows the disconnection next to what was the double bond. The only problem is how to make a monobromide from a symmetrical diol, that is structure 30. Sorry. Experiment showed that protecting one end of the diol, that is 30, as the tetrahydrofuran derivative, that is 31, gave good yields, and the monobromo compound, that is 32, was used to alkylate acetylene with the methyl group added later. Reduction and deprotection gave the E isomer of alcohol, that is structure 26, and the acetylation gave the pheromone, our target molecule, structure 25. In the previous presentation of alkene synthesis, we learned that the dienes could be made by the Witting reaction and also by the addition of vinyl lithium or Grignard reagent to ketone, followed by dehydration of the allylic alcohol product. Derivative of acetylene can do the same job as well. The first disconnection is the same, but a reagent for the synthon, that is for structure 40 here in this slide, replace the vinyl metal derivative. The published synthesis of structure 36 use the sodium salt, and the reduction goes in excellent yield. Only the dehydration of potassium bisulfate is little poor. Synthesis of ketones by hydration of acetylenes. A rather different reaction of acetylene is the addition of water, usually catalyzed by either you can take mercury plus 2 or give ketones. Terminal acetylene, that is here you can see structure 41, reliably give methyl ketones, that is for structure 44, as the intermediate vinyl cations, that is 42 is secondary. Water adds to the cations 42 to give the enol compound 43, which equilibrates to the ketone structure 44 with the loss of mercury acetate. The symmetrical acetylene can also be hydrated to one ketone, as two possibilities are the same. An intriguing example is the hydration of diol. You can see here structure 45 that presumably give the ketones, that is structure 46. This is not an isolated as under the condition of the reaction. Formation of cyclic ether, that is structure 47, is the faster comparatively with the hydration. In this connection, the very unsymmetrical acetylene, that is structure 48, with a ketone on the one side of the alkyne or triply bonded system and a cis alkene on the other, hydrates completely regioselectively to the diketone and gives structure 49. The involvement of the ketone in the intermediate, you can see here structure 50, shows why water add to one end of the alkyne and not the other side of the alkyne. We may have already seen above how the cis double bonded in the molecules of this sort can be made from alkynes, and so both main uses of alkyne appears here in this slide. Now, application of alkyne or acetylene in organic synthesis. The best application is an alkyne containing anti-AIDS drug. So we are going to discuss this connection and synthesis of anti-AIDS drugs over here. Merck's reserve transcriptase inhibitor Efavirenz, that is you can see here structure 53, is one of a new generation of anti-AIDS drugs. The disconnection of two structural C2O bonds reveals structure 54 that is clearly the adduct of an acetylene structure 56 and the ketone structure 55. Here the question is how to make this structure 56. So we have not yet met three-membered ring, but cyclization of carbon nucleophiles into CH2S with a living group, you can see in structure 57, works well. Now the question is how do we make the another structure, that is pentanol 58. The answer to the question of how to make the pentanol 58 is an exaggerated form of starting material strategy. We need a 5 carbon compound with some oxygenated and some unsaturation present in it. There is one exceptional cheap and abundant compound that fit in this condition, furfural, that is structure 59, when breakfast cereals are made. Furfural is an abundant byproduct, and the uh, Quaker Oats Company have patent on isolating it, but chemists can do so from corn crops by a simple recipe that gives 165 to 200 gram furfural from 1.5 kg of ground up corn crops. The treatment of furfural with aqueous NOH disproportionates the aldehyde into equal amount of acid, that is structure 60, and the alcohol, that is structure 61. No doubt the sodium borohydride would do the job better. Catalytic reduction gives this structure saturated alcohol structure 62 in 58% yield. Sorry, in 85% yield. We can see we seems not to be getting closer to 58, but 58 would actually result by dehydration of structure 62. In a real life, the alcohol 62 is turned into the chloride, and a double bond elimination with sodium amine uh, uh, gives a 58 structure after acidification. Though we saw elimination reaction used to make alkenes in a cheaper way using structure 15, this is the first we have seen to make alkynes. Now, three-membered ring can be closed after replacing the hydroxyl group by chloride by giving the treatment with two equivalent of butyl lithium. The first proton is removed from the alkyne so that the cyclization occurs on the dilithium derivative. If the cyclization is not worked up, the product is the alkyl lithium that can be added directly to structure 55 to give the alcohol, that is structure 54. In the Merck synthesis of efavirenz, this step is used to make a single enantiomer of structure 64, and this chemistry is discussed in a strategy and control. Well, this is enough from my side as far as this use of acetylene in organic synthesis is concerned. Thank you for paying attention to this video lecture. Keep asking question. As you know, the asking question is a beautiful way to get knowledge. Thank you.